In 1990, Jeff Elman published a paper called Finding Structure in Time. 60 pages showing a neural network could read a sentence one word at a time and remember what came before. The field had been waiting for this. A network that reads sequences, because language is a sequence. And for about 5 years, RNNs looked like the answer. They almost were. Almost. 2 videos ago, the 90-second neural network, Matmul, Squish, Matmul. 1 video ago, the 3 godfathers who kept it alive. This video, the first serious attempt to make one of these networks read text, word by word, left to right, just like you're reading this sentence. It almost worked, and why it fell short is the reason LSTMs and then transformers had to exist. Von gave us a feed-forward net. Input goes in one end, output comes out the other. Great for classifying a single vector, useless for a sentence. Because a sentence is not one vector, it's a sequence of vectors, and the meaning of word 7 depends on words 1 through 6. A feed-forward net has no way to carry information from step to step. It has no memory. Today's puzzle: if a feed-forward net has no memory, how'd we give it one? Elman's answer: a hidden state that gets updated every time a new word comes in. Same weights, applied again and again. Elegant, simple, and it worked for short sentences. But there's a specific way it broke on long ones. That's what we're here to see. Today's 3 beats. First, what a recurrent neural network actually is. The hidden state trick, Elman's 1990 architecture in one picture. Second, the vanishing gradient problem. Why RNNs forget. Not a bug, a mathematical inevitability that Sepp Hochreiter diagnosed in 1991. Third, what RNNs could do and what they couldn't. So the LSTM story next video makes sense. Beat 1. What an RNN is. Take the feed-forward network from Von. Now add one twist. At every time step, the hidden layer takes 2 inputs, the current word, and its own output from the previous time step. Same set of weights every step. That's it. That's the whole recurrence. Same network, applied once per word, feeding itself. Unroll that in time. Feed HE, feed cat, feed sat. Each step, the cell reads the current word and its own previous state, produces a new state, passes it forward. After 3 words, the hidden state contains, in principle, a compressed summary of everything the network has seen so far. Elman 1990 showed that if you train this on English text with next word prediction, the hidden state does learn to represent things like part of speech and syntactic category. Nobody told it to, it just fell out. For training, you unroll the network across the whole sentence and run backprop through the unrolled chain. Every time step contributes to the loss. Gradients flow backwards through every hidden state. This is called backpropagation through time. Same chain rule from Von, just applied along a longer chain. Longer sentence means longer chain, which is where the trouble starts. Beat 2. The vanishing gradient. Here's what happens when the chain gets long. At every step, the gradient gets multiplied by the same weight matrix as it flows backwards. If that matrix has values less than 1, the gradient shrinks. Every step, exponentially. By the time it reaches the beginning of a 50-word sentence, the gradient is essentially 0. The network can't tell what word 1 had to do with the loss at word 50. Sepp Hochreiter figured this out in 1991. As a master's student in Munich, his diploma thesis. Not published in English, barely read at the time. Bengio, Simard, and Frasconi wrote it up formally in 1994. Same result. Multiplying gradients through many time steps is doomed. Either they vanish if the weight is under 1, or they explode if it's over 1. Neither is trainable. The practical consequence: RNNs could learn short-range dependencies. 3 or 4 words back, fine. 15 words back, hopeless. Which means for a language like English, where the cat that chased the mouse that lived in the barn requires the network to remember the cat way at the beginning to conjugate was correctly, RNNs choked. Every long-distance grammatical relationship broke them. Beat 3. What RNNs could do. character-level language models, handwriting recognition, small machine translation systems, speech recognition front-ends. All of these short input windows, mostly local dependencies, RNNs, were solid. There's a famous Karpathy blog post from 2015. An RNN trained on Shakespeare, producing text that looks like Shakespeare. Local structure? Absolutely. Semantic coherence over a paragraph? No chance. What they COULT do? Anything requiring long-range memory. Document-level summarization? No. Coherent story generation over more than a couple of sentences? No. Question answering that requires connecting a fact at the start to a question at the end? No. And most damning, machine translation on long sentences. The exact task the field cared about most, RNNs, would translate the first half fine and then drift into unrelated words. So, the picture. RNNs were a real conceptual advance, a network that reads a sequence and updates a hidden state. Everything after them owes something to that shape. But the vanishing gradient meant they physically couldn't hold on to the past long enough to be useful for real language, which set up the exact engineering problem for the next video. Give the RNN a better memory. Make forgetting a choice, not an accident. That's the LSTM. 3 takeaways before the quiz. 1. An RNN is a feed-forward network with one twist. Same weights, same cell, applied once per word, feeding its own hidden state forward. Elman 1990 was the founding paper. That shape is the ancestor of every sequence model since. 2. Vanishing gradients. Multiply small numbers together many times. Get 0. Backprop through 50 time steps means the network can't tell how word 1 affected the loss at word 50. Hochreiter 1991. Bengio Simard Frasconi 1994. 3. RNNs were fine for short local structure, character LMs, handwriting, small mt. They broke on anything requiring long-range memory, which is why the LSTM had to exist. Quiz 1. What is the core structural difference between a feed-forward network and an RNN? A. RNNs use real, feed-forward networks use sigmoid. B. And RNNs. Hidden layer takes both the current input and its own previous hidden state, with the same weights reused at every time step. C. RNNs have more parameters than feed-forward networks. Or D. RNNs run on GPUs. Feed-forward networks run on CPUs. B. This is the entire recurrence trick. Same weights, applied once per word, feeding the hidden state forward. Elman 1990. That one change lets a network read a sequence instead of a single vector. Quiz 2. Why do vanishing gradients wreck RNNs on long sentences? A. The GPU runs out of memory. B. Gradients get multiplied by the same weight matrix at every backprop through time step. So if that matrix's values are under 1, the gradient shrinks exponentially and effectively becomes 0 for early time steps. C. The tokenizer breaks. Or D. The learning rate is too high. B. This is the exact math. Hochreiter 1991. Bengio Simard Frasconi 1994. Multiply by less than 1. 50 times, you get 0. The network literally cannot see how word 1 affected the loss at word 50. Quiz 3. What kinds of tasks did RNNs handle well before LSTMs? A book-length summarization and coherent multi-paragraph generation. B. Short window. Mostly local dependency tasks, character-level language modeling, handwriting recognition, speech front-ends, small machine translation. C. Nothing at all. RNNs were purely theoretical. Or D. Only image classification. B. RNNs were absolutely useful for local structure. Karpathy's 2015 blog post showing a character-level RNN generating Shakespeare-style prose is the classic demo. The failure was long-range memory, not the whole idea. Back to the puzzle. Lecture 6 is the story of how a simple stack of matmuls scaled into GPT RNNs were the first sequence architecture. The right shape, a hidden state that gets updated, but the wrong dynamics, memory that leaked. Next video, the engineering fix. Gates, explicit control over what gets remembered and what gets forgotten. The LSTM. Next time, LSTMs, Two researchers in Munich, 1997. They added 3 gates to the RNN cell: input, forget, output. That one change made networks able to remember things across 100 time steps. The world ignored the paper for 15 years. Then Google Translate switched to LSTMs overnight. Hit subscribe.